Okay, so we are going to start double displacement reactions. So double displacement. What I mean by double displacement reaction is earlier we were dealing with one element and displacing the other element. Now we will be seeing some interchange of both the cationic part and the anionic part. Okay, so double displacement will look like something like this. When a compound is AB reacting with CD, and I'm assuming the first part is the cation and the second part is the anion. So the cation of this is going to react with anion of this, so it will form AD, and the cation of this is going to react with anion of this, or will take up this one, and you will get this product. So what we are doing, we are actually interchanging the ions. Okay, you cannot change both the ions, otherwise it will be again, if you are interchanging with A and this with D, again you will get AB. So this is not the case now. You have to interchange one of the ions, so it will be two different compounds. So if I take A and I will take D, so again automatically B and C will come together. And since I have assumed that the first part should be the cation part, that is why I have written C before B. Okay, nothing more than that. It's very easy. So double displacement reaction, what does it involve? It involves exchange of ions. It involves exchange of ions. You can say this has exchange A, or B has exchange A, or you can say A has exchange B, whatever. Exchange of ions is going to take place. Exchange of ions will be there. Okay, so they can be classified into two types, two groups basically. The two types you can say. The first one is acid-base reaction. Or we say it is a neutralization reaction. Okay. And the second one is precipitation reaction. So we have covered some part of this precipitation reaction in our earlier class. We were talking about the different colors that we are going to get. So precipitation reaction. So we will be covering this topic in more detail here. So based on this, we will be talking about two reactions, neutralization reaction and precipitation reaction. These two reactions are very, very important. So what we can expect, let us first take up acid-base reactions, and then we will take up the precipitation reaction. Okay. Now, what is acid-base reaction? First of all, what is an acid? What is a base? Acid and base. So, first of all, let us try to understand what is an acid, what is a base. Okay. So normally we think, okay, the best definition or the most common definition is acids are H plus any proton donors and bases are hydroxyl any OH minus donors. Okay. So we will be covering that thing also in detail. So there are three different theories are there. Three different theories. There may be more, but we will be talking about three theories. Okay. The first one is called as Arrhenius theory. He classified acids and bases something like that. Acids are basically proton donors. Proton means H plus. They are proton donors. Whereas the bases are hydroxyl donor, that is OH minus donor. This is what we normally think at your level. So please understand, we have to classify acid-base reaction based on the reaction given. So we will not say that, okay, as the theory is good for acid, but it will be different for a base. So we should think in this regard that it should be simultaneously, it should satisfy both the conditions, acid being a proton donor and base being a hydroxyl donor. Then we will say it is a Arrhenius acid base pair. Arrhenius acid base pair is simply tells that acids are proton donor and bases are bases are hydroxyl donor. Okay, examples, we can say acid can be HCl, H2SO4, H3PO4, many acids. You must be knowing all this. HNO3, even acetic acids, weaker acids also. So they are basically H plus donor. That is why bases must be hydroxide. It can be sodium hydroxide. It can be potassium hydroxide. It can be calcium hydroxide. It can be barium hydroxide. They are comparatively stronger. And it can be, you can say, ammonium hydroxide, which is relatively weaker. Okay, this is the first theory. So what we will say? We will say, okay, an acid-base pair can be regarded as Arrhenius acid-base pair if it satisfies the condition acid being proton donor, base being hydroxyl donor. Okay, this is the first thing, and I think this is the one which you have read earlier. The second definition, that is Bronsted acid-base pair. Bronsted, let me remove it. Bronsted acid-base pair. Bronsted Lowry concept of Bronsted acid-base pair. Here, there's some difference. Here, acid will be regarded as those substances which are proton donors, which is exactly same as the Arrhenius acid, proton H plus donor. Whereas base here is something different. It is proton acceptor. Okay, let me give an example. Suppose I have ammonia reacting with HCl, and we know that HCl is an acid, ammonia is a base. What actually happens is there is no OH present here, so it cannot be Arrhenius base, but it accepts H to form NH4 plus Cl minus. So HCl has donated its proton, that is H plus. So it is a acid, Bronsted acid, as well as Arrhenius acid, we can say. But looking at the base part, we see that there is no OH minus present, so it cannot be Arrhenius acid base pair. But since base ammonia has accepted the proton to form NH4 plus, therefore we will regard this base as Bronsted base. So this system will be Bronsted acid base pair. Is it okay? Clear? Bronsted acid base pair. So ammonia is one, we can have phosphine, pH3 is one, which can react like this also. Okay. So reaction with acid base is something proton donor and proton acceptor wise. This is the second one. The third theory that we should learn is Lewis acid. So what is Lewis acid? Lewis acid base pair. The third one is Lewis acid base pair. Here, acids are regarded as lone pair acceptor. Lone pair means non-bonded electron pair. Non-bonded. That is, they are not a part of any bond. And bases are regarded as lone pair donor. Lone pair donor. Okay. Let me give an example. Here, ammonia and BF3. Suppose this is BF3, boron trifluoride. And here we have ammonia. It contains one pair extra which can be donated to the boron. So it is going to form another new bond, NB bond. So here 3F is already present. I am writing this on the left side and this one on the right side. You can write like this. The electron pair has been donated. So we will put arrow like this. This is called as coordinate bond. Coordinate or dative bond.
So what do those two dots represent?
The two dots means there are two electrons which are actually not the part of any bond. They are free to be donated. We will cover this topic in chemical bonding, where we will see that a bond is formed, a covalent bond is formed by sharing two electrons, that is one pair. So here these two electrons are coming from the nitrogen. They have been given to boron. So two electrons are there. So these two bonds are there. So this two electrons will form a bond. This bond is something unique, which is called as coordinate or dative bond. Coordinate or dative bond. Okay, we will cover this thing, don't worry. So first of all, let's try to understand now what are the possibilities, what are the acid base pair that we should know. It's not only NaOH plus HCl gives salt and water. So in the next two cases, the last two theories, you'll find that hardly any, in this one, there is no water. There is no water. Even there is no sort of salt also. Something, a very unique thing has formed. Okay. So when we say that acid plus bases give salt and water, we normally talk about Arrhenius acid base pair. Am I clear? When we are talking about acid plus base giving salt and water, we are definitely talking about Arrhenius acid base pair. Is it okay? Any issue? This is a commonly accepted definition of neutralization reaction, but you must understand that it is not limited to acid base pair, Arrhenius acid base pair. There are other definitions where there is no salt or there is no water present. Okay, so that is what I wanted to make it clear, that you should not blindly follow all this. Just try to argue which can be the possible definition or theory behind the acid base pair that you are predicting. Okay, so the reactions of ammonia will be more often something like this. It will be something like Lewis acid base pair, or something like Bronsted also. You've seen Bronsted also. Bronsted acid base pair. Okay. So these three are the acid and bases in our book. In NCRT, we have to follow the Arrhenius concept, and which is what? That is OH minus donor and H plus donor should be present to qualify for Arrhenius acid base pair. So when I write this thing as H plus donor, shall I am going to write this as HA. HA means A is the negative part of the acid and H is the H which is going to be donated. And if I write B base as BOH, so B is the positive part and the OH is the hydroxyl ion which is to be donated. So I'm taking like it can be HCl, H, HSO4 minus, H2, SO4. So anything, this is your A part, this is your A part, this is your A part. Okay, it can be 2H, it can be 3H, whatever. I'm just writing HA. Similarly, BOH also. So what is the product here? When they are going to combine, since it is a double displacement reaction, the cation of the acid should get the anion of the base and vice versa. So we will have a formation of Ba plus water. Since both are electrolytic in nature, this is a salt that we are talking about, where B is the positive part of base and A is the negative part of the acid. So this is the salt. So you can see the formation. The cation of the salt has come from cation B has come from base, and the anion, that is A, has come from acid. Okay, very easy, very easy. Okay, so these are basically the concept which is involved in this. Now, since we have written H2SO4 in two forms, HSO4 minus and SO4 2 minus. A can be HSO4 minus and SO4 2 minus. So we have to take care how many H plus are being donated. So next concept is basicity and acidity of a base, basicity of an acid and acidity of a base. So first of all, let us take some examples first and then we will try to understand. Let me take example. BaOH whole twice plus HCl. BaOH whole twice plus H2CO3. Write the product. Identify the positive part, which is Ba2 plus. So this is your Ba2 plus is the positive part. Identify the negative part of the acid, which is Cl minus 1. Cl minus. So both will form what? It is going to form BaCl2 plus water. Okay. Again, identify here. It is negative part and positive part. Barium is the positive part, Ba2 plus, and here you will get carbonate and CO3 2 minus. So what you will get? You will get BaCO3 plus H2O. Okay. So two different parts have to be very clear.
Yes, sir.
We can take more examples. Just try to predict the product in each case. I'm removing all this. So, question, predict the product in each case. In each case. Assume complete neutralization. That means there should not be any H or OH remaining. It should be converted into water. Okay. So let us take HCl as the first one and try to react with NaOH, NH4OH, calcium hydroxide, magnesium hydroxide, do it. Can include one more, zinc hydroxide.
So done.
Done? Okay.
Yes, sir, done.
So very easy. We have to identify the cationic part and the anionic part. Cationic part is here is Na. So I will get Na and here the Cl, so NaCl plus water. Here cationic part is NH4 plus here Cl, so NH4Cl plus water. Here calcium hydroxide is there, so it is 2. And here it is HCl. So cationic part is calcium and the anionic part is Cl, so CaCl2 plus water. I'm least bothered about balancing, we will do it afterwards, don't worry. This one, magnesium hydroxide, so magnesium will be the cationic part and the anionic part is this one, Cl.
Yeah.
So MgCl2 plus H2. What about this one? Cationic part is zinc and the anionic part is Cl, that is Cl2 plus water. Very good. This is one very important reaction. Now let me change it to some other, let us say some other acid, H2SO4. And again try this with H3PO4. And I already told you to don't think of that any H is being left because this statement clearly says that assume complete neutralization means all the H must be consumed. Do it fast, very easy. Let me run this. None?
So I'm done with H2SO4, just doing H3 pure.
Last
Okay,
one.
do it first, do it first. So I'm writing the products of sulfuric acid. So it is Na plus and sulfate is 2 minus. So these two will be again combined. The formula will be Na2SO4 plus H2O. Here it is ammonium sulfate plus H2O. Here it is calcium sulfate plus H2O. Here it is magnesium sulfate, okay, plus H2O. And finally, here it is zinc sulfate plus H2O. Very easy. Okay. Now think about phosphoric acid.
So by the way, for phosphoric acid, if it reacts with NaOH, the product will be Na3PO4
Yeah.
plus H2O.
So if I am writing the product for this one, I should write PO4 3 minus. So it will be Na3PO4. Sodium phosphate. Again, here it will be, if I just write it for this, it will be Na3PO4. This will be Ca3PO4 whole twice. This will be Mg3PO4 whole twice. Zn3PO4 whole twice. This is the answer. We will be taking up the balancing part. Don't worry, it is very easy. It is very easy. How we can do it? Just understand one thing, only one thing, and you can easily balance this type of reaction. So in this reaction, what is going to happen is, in Arrhenius acid base pair, what is actually happening is the reaction is actually taking place between one H plus and one OH minus, giving one water. Okay, so the reaction is actually this one. Somebody is giving you H plus, somebody is giving you OH minus, and both are combining to give you one water. One H plus plus one OH minus will give you one water. This is coming from acid. This is coming from base. Acid, base, acid, base. So how to balance this? We have different coefficients. How to balance it? Balancing is very easy. If you say, if I say that number of H plus coming from the acid is, suppose, VF acid. Why I'm saying VF? I'm saying it's a valency factor. I'm just introducing a new term called valency factor, also called as N factor. Okay. What it represents? It represents how many H plus is actually coming from the acid. Second part is OH minus. Suppose I should write VF, valency factor B. VF means valency factor. It is important when we will talk about equivalent weight, molecular weight, and so on, moles and equivalents. So when I'm saying that, first thing, let us try to calculate the valency factor or the N factor, also called as or N factor. Whatever. Okay. It's a general term. We will now understand. We will say this term was also called as basicity of an acid. This is a we are talking about some particular term, basicity. In acid, we will say basicity of an acid. In base, we will say it is the acidity of a base. Okay. So valency factor and factor is more common. We will be dealing with this till class 12th. We will be talking about valency factor of redox reaction also. We will talk about valency factor for many other reactions. And in particular, acid-base reaction, this valency factor will be also termed as basicity of an acid. For base, it is acidity of a base. So what does this represent? It represents basicity means what? Basicity of an acid is the number of H plus donated by the acid in that particular reaction. So please understand, it must be defined as per the reaction. If nothing is written, if nothing is mentioned, then we will assume complete reaction. Then we will assume complete neutralization. So all the H and all the OH will be consumed. That is what we are expecting. So somebody says, okay, basicity of H2SO4 4 is, by asking this and he is not giving anything else, you will assume, okay, he wants that everything must be complete. So the maximum basicity must be 2 because it contains 2 H plus which can be ionized. Okay, so this is important to understand what is basicity of an acid. Okay, in general we'll talk about valency factor and factor, but particularly for an acid we will talk about basicity of an acid. If we modify suppose let us take an example first. Example, in a molecule, if you take HCl, we have just only one H per molecule. Please understand what is there. By I should write by one acid molecule. One acid molecule. Per molecule, how much it is given? Okay. So HCl contains only one H that can be ionized. So basicity will be 1. Is equals to 1. If we have H2SO4, then we have a choice whether it is going to give you 1H or 2H. But since nothing is given, again we will say, okay, nothing is given, so we will take basicity. Maximum basicity is equals to 2. PO4, nothing is given. Okay, then again the basicity will be maximum. We are assuming to be 3. Okay. So this is the simplest cases that we are going to deal with.
Yes.
Okay. But there are some problems also. Let's write one question. Do we mean that basicity of an acid is equal to the number of hydrogen atom present in the molecule? Do we mean that basicity of an acid is equal to the number of hydrogen atoms present in the molecule? Question mark. What does it say? So you're saying, okay, 1H, 1, 2H, 2, 3H, 3. Is it always the case? Not a strict.
No,
No,
sir.
sir. No, sir.
Okay, very good.
No, sir.
Very good. Let us take examples to understand. Answer
So
is
does it depend? So does it depend on the ionization of the acid?
yeah. Yes, very good. So it depends. Although the reaction is complete, but we are talking about ionizable hydrogen atoms. So when we talk about basicity, you say no. Just write no. Basicity talks about ionizable hydrogen atoms per molecule. Okay. Not every hydrogen can be ionized. Not every hydrogen can be ionized. In general, if you talk about this, suppose example, let us take example. Boric acid, formula H3BO3, we have 3 hydrogen, but basicity is equals to 1. Even that H is coming from water, not from here. So boric acid is very particularly, it's not Arrhenius acid. Please understand, it's not Arrhenius acid, but it is Lewis acid.
So I just had a question.
Yeah,
So is boric acid a weak acid?
yeah, very weak acid. You can apply in your eyes. You can apply on the on your wounds. So it's definitely it must be weak, isn't it?
Yes, sir. So basically, less basicity means less ionization, which means it's weak acid.
Okay. Less ionization, yeah, very correct. Less basicity is wrong term. Basicity does not mean that it is weak or strong. It simply means how many H plus you can give. Suppose I am saying if you are given 100% freedom that you can ionize if you can, then how many H or OH you can give. Here, if you leave this thing alone, if you try to react, then all these H are so strongly bonded that they will not give you H. So how come this becomes an acidic? It becomes boric acid is unique because it will say, okay, I am not going to give my H. It will react with water. What water? Let me have some stomach on H of water to make you understand. It will say, okay, my H is very secure. It's like something like America is having all the petrol reserve and it's going to buy from somewhere else. Okay, having everything, fuel reserve is there, but it is again going to buy it. It will say, okay, please, I'm not going to give you H. I'm not going to give you H. I am going to react with water to form BOH whole 4. So it can be written as BOH whole 3 also. This is the same thing, isn't it? It will react to form BOH whole 4 and it is again going to give you H plus. This H plus is coming from water, so again star mark is there. So this is the case. Boric acid is not going to give its own H. It is going to take OH from the water and the remaining H is left alone. That is why one molecule is going to give you 1 H plus. That is why this basicity of boric acid is taken to be only 1. It is not considered as Arrhenius acid. That is a very, very important point for NTSC examination also. Okay.
Yes. So nothing I understood.
Yeah. Okay. Any question till now? It's very important concept.
And so barium's valency is 4 in this case, yeah?
Valency.
Yeah, like what's barium's like in
We
the
will talk
product
about
it was
valency later on. We are talking about covalency. Yeah, it's 4. So it is forming
okay.
4 covalent bonds here.
Okay,
Okay.
yes, sir.
It's called covalency. Okay, so this is a unique case of boric acid. We must remember this thing. I think you must have played carom, and there you can use some boric acid powder. It's very, very slippery. So it's crystal form.
Oh,
You will be amazed. The striker will keep on rebounding. Okay, it's fine. Very, very thin crystals are there. Okay. Another case, let us take acetic acid, CH3COOH. It is called acetic acid. Also can be written as C2H4O2. It contains 4H, but basicity is just 1. Only one H plus can be ionized. Okay. Then H3PO3, phosphorus acid. Phosphorus acid. It can give you only 2H, not 3. 2H, not 3. So basicity is 2, not 3. Please understand. Not 3. So it contains 3, but it is the ionizable H is only 2. It is not 3. It contains 4H, but ionizable H is only 1. It is a weak acid. It is also a weak acid, comparatively weaker acid compared to HCl, HBr, and so on. So you can easily understand. So there's no such guarantee that all the H will be ionized. Okay, so very easy to understand. Provided you know the structure of this. So how to understand this thing? How to take a note of it? Why it is happening so? So there we are going to talk about. We will be taking up this topic later on. We will divide the acids into 2 parts. One is hydroacids, another is oxyacid. That will I will cover my next or after some lectures. So that is very, very important. And there you will learn why the ic, us, ide subscripts are used. Why hydrochloric acid? Why chloride ion? Why nitric acid? Why nitrate ion? ATE, ITE, sulfurous acid, why sulfide ion, ITE. Okay, so there is a logic behind the naming of compounds, naming of acids. Okay, so here we are going to talk about the structure part of it. I will draw it here, just draw it, and we will discuss all the this part, how it is going to react, and which hydrogen will be ionized in any oxyacid. We will be discussing this thing later on. Okay, so let me draw the structure of H3PO3 first. It's a curious case. It's important to understand. So let us try to understand what I mean to say is.
Sir, my charge went out on fifth. So did you write anything phosphoric
No.
acid?
Structure of S3PO3. The structure of S3PO3 is nothing like this. We have P, 1, 2, 3, 4. 4 bonds are there. Here it is double bond O. Here it is O. Here it is O. H, H, H. So there are 4 bonds here. 1, 2, 3, 4. Total 5 bonds because there are 2 bonds here. But there are 3 oxygen 1, 2, 3. There are 3 hydrogen 1, 2, 3. So which hydrogen can be ionized? This hydrogen attached with oxygen can ionize. This one can be ionized, but this one cannot be ionized. This is non-ionizable hydrogen. So these two can be ionized, but the third one is non-ionizable. Therefore, the basicity of phosphorus acid is taken as 2, not 3. Okay. But if you take the H3PO4, you will see double bond O, 1, 2, 3, double bond, O, 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 H, H, H. There are 3 H here, 3 H here. All H are attached to oxygen atom. So all the H can be ionized. So all the H can be ionized. This H, this H, this H can be ionized. So the basicity 3. Here basicity is equals to 2. Okay. So what we are learning is that in an acid, which we call it as oxy acid, which contains oxygen, hydrogen, and some element. So what we are saying is, let's write it down and then we'll write the lines and then we'll summarize it. Now, write it down clearly. In an oxy acid, OXY, ACI, in an oxy acid, that is acid containing, hydrogen, oxygen, and one other element like phosphorus, sulfur, chlorine, carbon, nitrogen, etc. One other element. So there will be hydrogen, there will be oxygen, and one other element will be there. Boron. Okay. The number of ionizable H, is equal to the number of hydrogen atoms directly attached with oxygen atom. Exception is boric acid. Okay. All other hydrogen atoms are generally non-ionizable. All other hydrogen atoms are generally non-ionizable. Okay. So now we have, these are not very exceptions. Please understand. These are just the structures the nature has produced. You are just seeing the formula and you are predicting basicity equals to 3. But the structure says something else. There is a pH bond, not the OH. It's not OH. But whenever there is a OH, it is ionizable. H2SO4 contains 2H. Both are ionizable because both are attached to the oxygen atom. Am I very clear? Am I clear? Okay, so we have completed acid-base reaction in great detail, and what we was talking about is the balancing part of it. Okay, so once we know what is the basicity, similarly we can talk about acidity of a base also. It is the number of OH minus donated per molecule of base. Okay, let me first finish that also before closing the things, winding up. Let us finish this. So the last part of it, we have discussed the basicity of an acid. Let us talk about acidity of base. What is this? It is the number of ionizable, and we are talking about Arrhenius base. So OH minus per molecule of a base. Per molecule of a base. For example, calcium hydroxide, the acidity is 2. Sodium hydroxide, acidity is 1. Aluminium hydroxide, acidity is 3. So this is the maximum. If nothing is given, we should talk about maximum. If something reaction is given, then we should talk about the reaction. Okay. This is the acidity of a base. And how to balance it, please understand. What I was saying is acid plus base give salt and water. To balance this reaction, first compute the valency factor of acid, compute the valency factor of base, and cross multiply. Multiply here and multiply here. Okay. Once you get the coefficient here, you can easily get the water here. The number of H converting to OH, reacting with OH, you can know it. Cross multiply, get the value, you will get the answer. For example, suppose I have NaOH and H3PO4. So I know the valency factor of this is 3 because it is containing 3 hydrogen. I know it is 1. So cross multiply, you will see that 3 NaOH plus H3PO4. Now you know what is the ratio of the coefficient. Now product will be Na3PO4. Very easy. And water. So this is fixed, so it must be 3. So 3 Na is already fixed here. So only thing we have to take water. So how many H is there? 3. So yes, there must be 3 water. Okay. How many H? Whichever is written, just take it. Since 3 H is there, 3 H plus is there, so 3 water should be formed. Is it okay? Very easy.
Yes, sir.
Okay. Let me take one more example. CaOH whole twice plus H3PO4 again. I know that its basicity is 3, its acidity is 2, cross multiply. So what you will get? You will get 3 times and 2 times. So this is fixed. We know that calcium phosphate is formed Ca3PO4 whole twice. So again calcium is gone. Only thing is how many hydrogen atoms are there? 6 H plus is there because 3 per molecule into 2 times 6. So 6 water will be formed. I think it's very easy to balance now. Is it okay?
Yes, sir.
Okay then everybody. This is over from my side. I hope you've enjoyed, you've learned many things.
Yes, sir.